Hello, everyone. Thank you for being here. So I'm Paul Hargous, a PhD student in physical oceanography. My supervisors here are Vincent Combe and Ananda Pasquale. And I will present to you the study entitled "The Mediterranean is Steering, Satellites Reveal a Rise in Eddy Kinetic Energy." But first, I will start doing an introduction, talking about why we study the ocean, why we are interested in the small scales, the mesoscales, and an introduction about satellite altimetry. So first, some key figures about the oceans that you may probably know. So it produces oxygen and it's a sink for heat and carbon dioxide. So basically, it helps regulate the climate on Earth by transporting heat and carbon from low to high latitudes, thanks to the thermal aligned circulation, tides, winds, etc. So how we study the ocean? We have different types of data sets. First, in-situ data, like gliders and moorings, that allows to have data in a specific point, or even allowing to have some profiles using the gliders. We also use modeled data that allows to have three-dimensional data and also to make some forecast or to discriminate the forcings, doing some experiments. And finally, we have satellite data, which I will present because my study is only using satellite data. And these data are useful as they are global data. So a bit of history about altimetry missions. So satellite altimetry started in the early 90s. And now we have more than 30 years of data, which is really useful to study climate variability. And so those satellite altimetry missions have these satellites have different orbits, so different characteristics, because there is, in fact, a compromise between spatial and temporal resolution. For example, the Topex, Poseidon, and Jason missions have a 10-day cycle repeats. And as you can see, they don't cover the area around the poles, and they have a coarse spatial resolution. And on the other side, some other missions that have a longer repeat cycle, 27 days, are able to cover the poles and have a much thinner spatial resolution, but have a longer repeat cycle. So we need to overcome this problem. It's necessary to use different missions to combine them in order to have a better data set. Or if you have been to a president seminary from someone of my group, you probably remember about the famous SWOT satellite, which can provide some two-dimensional data, and it's part of a solution to overcome this problem. So how satellite altimetry works? So basically, it uses the relation between velocity, distance, and time. So the satellite sends microwave radar pulse towards the ocean surface, and it bounces back to the satellite. So the satellite measures the range here R, and knowing exactly the altitude of the satellite using technology called DORIS, for example, we are able to determine the SSH, sea surface height here. And having many years of data of SSH, we are able to determine the mean sea surface, MSS, basically 20 years of data. And having this mean state, we can determine the sea level anomaly by retrieving from the sea surface height the mean sea surface state. So altimetry allows us to have the sea level. But I told you that my study is about eddy kinetic energy. So kinetic energy, to compute it, we need the velocities. So how do we get the velocities? Starting from the sea level anomalies, we use the geostrophic approximations. So basically, it assumes that there is a balance between the Coriolis forces and the pressure gradient. So the Coriolis forces are due to the Earth's rotation and the pressure gradient to the SSH differences. So thanks to this relationship, we obtain the geostrophic velocities, which is a good approximation in the open ocean and explain most of the dynamics. And with these velocities, to study the dynamic of the ocean, we compute the kinetic energy. And the same as for the sea level anomaly, with the geostrophic velocities, we are able to define mean state and the anomalies, the geostrophic velocity anomalies. And when we compute the kinetic energy using those velocity anomalies, we have the turbulent kinetic energy, which is called eddy kinetic energy because it is associated with eddy-like motions. So an eddy, just so you know, it's circular movement. It can be cyclonic or anticyclonic. So now that you know more about how we obtain this data and we arrived to compute the eddy kinetic energy, I will start giving to you a bit of the context about how we started this study. So the EKI, eddy kinetic energy, it's a common metric to determine the mesoscale variability, which is the scale of exchanges and transport of different characteristics in the ocean. And so we can have it using satellite altimetry. As you can see here in this map from Renaud et al., that the most energetic area are the western boundary currents, here the Hargous currents or the Kuroshio currents here. And some recent studies have shown that there is an increase in eddy kinetic energy, so positive trends using satellites and model data. But the satellite data used in the studies are built using all the satellites altimetric missions available. So as I told you, one way to overcome the problem between spatial and temporal resolution is combining different satellite missions. And the dataset used here are built using all satellites. So starting with 2 satellites at the beginning of the 90s, up to 7 satellites in the last years. But however, when we compare those trends from the all satellite product to the 2 satellite product, so satellite product is built using a stable 2 satellite constellation along the time, we observe some big differences in the trends of eddy kinetic energy. Still, both are positive, but the differences are quite big. So those studies have been done at a global level in the most energetic area. And here we are interested in the Mediterranean Sea. And so the trends during the altimetric record. And we will also investigate the influence of the dataset product. So the dataset we used 3 datasets, all freely available online on the Copernicus Marine website. We use 2 all-satellite products, which I call AllSatMed and AllSatGlow. So this one is a European product with a thinner spatial resolution than this one, which is a global product. And finally, 2SatGlow, which is the same as this one, but using a stable 2-satellite constellation. Concerning the methodology, as I told you, calculating the EKI, we use the geostrophic anomaly velocities. And for the trends, we used a modified Mann-Kendall test. So here, first, I show temporal mean of eddy kinetic energy over the Mediterranean Sea during the altimetric record. So to give you an idea about the order of magnitude here, I don't know if you remember at the beginning, but we had values around 3,000 square centimeters per second square in the most energetic areas in the ocean. And here we barely arrive to 500. So it's up to 6 times lower than in the most energetic areas. And the most energetic areas in the Mediterranean Sea are on the western side, the two gyres of the Alboran Sea, and on the eastern side, around the Petra eddy here. We can compute the spatial mean of Eddy Kinetic Energy. So this one is using the all satellites global product. So we can see a season, an annual cycle, and when we compute the trend, we obtain 0.9 squared centimeter per second squared per year. And if we compare these trends to the two satellite trend, we see that the satellite signal and the all satellite have the same interannual variability and seasonized cycle, but the trend is much lower, up to 5 times lower. And finally, for the last product, the AllSat European, it's closer to the AllSat Global and a bit higher because it has a better spatial resolution, so it allows to resolve smaller scales. So here we compute the difference between the AllSat Global signal and the TwoSat Global. So between the yellow one and the blue one, we obtain this curve. So we see an increase along the time, but not a linear increase, but more step-by-step increase, which appears to be highly correlated with the evolution of the number of satellite altimetry missions, 0.87. And from the time we have 5 satellites, we see that it increases slower. So what we did, we performed a second-degree polynomial regression between this difference and the number of satellites in order to discriminate the contribution of each satellite, and removed it from the all-satellite global curve to obtain this green curve. So the idea is to have the all-sat global without the influence of the evolution of the number of satellites. And it's much closer to the two-satellite global signal. Here it's a synthesis of what we obtained in the Mediterranean Sea. So the time series I've shown you and the trends. So now we will focus on the most energetic areas, which are on the west, the Alboran Sea here. And we observe similar results as for the Mediterranean Sea, but with bigger trends and bigger differences, as it's a more energetic area. And so when adding satellites, we're able to see more energy. And on the other energetic area, the Petra eddy here, so it's the only place in the Mediterranean Sea where we have negative trends. And we can see, so yeah, we have big negative trends, and we can see that all products show more similar results concerning the trends. So this can be explained by the fact that the area here is smaller and it is crossed by 2 satellite tracks. So there are less differences due to the interpolation when building the data set. Or here the variability is lower than the time series I've shown before. So the 2 satellite product is able to better capture the sea level. And also the values of Eddy Kinetic Energy are higher than before. So the artifact due to the number of satellites is less important. And what we see here also is that the intensity of the Petra eddy have decreased a lot these last few years. We're having some peaks at 1,500, and here barely to 500. So to conclude the study, the all satellite products probably overestimate the Eddy kinetic energy trends in the Mediterranean Sea, but what's important is that all the products show a positive trend, so an increase in Eddy kinetic energy, and we should take care when studying climate impacts on which satellite dataset we use, because the number of satellites does have an influence when we compute Eddy kinetic energy trends. And when we study smaller areas like the Europetra area, we have more compliance between the products. So it's because also the track's configuration is adapted to the structure. So it's important to maintain the altimetric record and to think about the tracks of the satellites. Thank you for listening, and that's it for me. If you have any questions. Yes.
Thank you for this very interesting presentation. I like the overlap of the number of satellites and this trend. It was very conclusive. And I have one question. What is the implication of this increasing eddy kinetic energy? So now you confirm this energy is increasing, and what is the implication on the human world, let's say, or on the biology, or what can be effects of this?
Well, the increase of Eddy kinetic energy also have implication is so the eddies have implication is in the vertical movements, which brings rich waters to the surface. So it's also a change in the Eddy kinetic energy can change the currents and the places where there are some nutrients, for example. Also an increase in the Eddy kinetic energy in the big structures like the Gulf Stream can have impacts as it increase the horizontal gradient between the poles and the equator in temperature or in density, so it changes the movements of the water, of the current.
So yes. It also can impact climate at the end. It can impact local climate at the end.
Yes, like I don't know if you've heard about some studies telling that there is the AMOC is slowing down, and so this can have, I'm not sure about the real impact or if it's true or not, but the impact that are told is that, for example, we'll have a big cold in Europe due to this slowing down of the AMOC. So yeah, it has climate impact locally or globally, for example, for the Gulf Stream. Yes.
So essentially, it's related to the next question. So if I understand well, the majority of the workpiece that you were studying is localized in the Albaran Sea, which is the mouth of the Mediterranean. So I was wondering whether there is going to be an impact in the exchanges between the Atlantic and the Mediterranean because of increases in the currents.
Well, for sure, the difference is in the changes in the Mediterranean Sea will have repercussion at a global scale because of this connection between the Mediterranean Sea and the Atlantic Ocean, and also there is a change in as there is a change in the Gulf Stream, there are also changes in the input of waters in the Mediterranean Sea. So there's a would say there's an impact of the Atlantic Ocean in the Mediterranean Sea, and also about the waters that leave the Mediterranean Sea towards the Atlantic Ocean. So yeah, both are all linked and have impact on each other. Then precisely what will be the impact, I can't tell you now. Yes.
When you complete your anomaly, your Eddy Kinetic Energy anomaly, you use, I guess, all data, right?
Mm-hmm.
To complete the anomalies. So, but the data is not consistent because you have sometimes 2 satellite products, sometimes 3, sometimes 5. So how you can deal with this?
For the all satellite product, you mean?
When you compute the Eddy Kinetic Energy anomaly, so you need the anomaly, so you
Mhm.
compute the anomaly in time. Each point of your domain.
Yeah, so I have like in the data set, they provide already geostrophic velocity anomalies using as a reference 1993 to 2012. And so what we did is compute the anomalies for the entire time, so from 93 to 2023, computing the mean and retrieving it from the geostrophic velocity to have the anomaly. I don't know if I answered your question or not. Yes.
What is the impact of the sea level rise on these results? You try to detrain the sea level to compute the velocities before computing the EKI, because it might have an impact on this EKI trend you have. And the EKI here is not only the mesoscale, but might be also changes, lower changes of the mean circulation.
Well, we didn't retrieve the sea level rise trend from the velocities first because in the level 4 data, so it comes with the velocities, so we use them. And concerning the level 3 data, when we computed the Eddy Kinetic Energy, no, we didn't retrieve the sea level rise trends. Maybe it can be a thing to retrieve it. I don't really know. Because when we computed when we have a long track data here, what we can compute is the perpendicular velocity, thanks to the formula I showed you before. And so using the sea level anomaly, we compute the perpendicular velocity, and we can have the perpendicular Eddy kinetic energy. And what we see here is that, so these curves here, we don't have a lot of we have similar trends for all the products. So the all satellite global, to satellite global, and the all satellite European compared to the level 3, we had really similar results. Probably retrieving the sea level rise trends. I don't know if it will change. I'm not sure. Any other questions?
It's just a curiosity, but maybe what's your next plan with this? And also I have one question. So you could now, or the idea you could now try to find the correlations between, so you have now this increasing trend of the Eddy kinetic energy, and which is the main impact factor to it. Like if you try to fit it with sea surface temperature or any kind, I'm not the oceanographer. So I don't know which parameter it could be the one.
Well, the idea to go further was to study, so this increase also could be caused by the winds or the increase in stratification due to the climate change. So there are higher horizontal gradient, and so we were studying the changes in the winds around the European region here, because what we saw here, it's an important decrease in the intensity of this eddy. So it's a non-permanent eddy, but here we clearly show that we clearly see that something is happening around this eddy. So we were studying the winds in this area.
One last question. So what is the time scale for the normal eddy to, let's say, from turning clockwise or cyclonic to anti-cyclonic, or what is the normal life cycle of one eddy? Because there we can see it's like 1 or 2 years.
Depends, like there are some eddies that for few months depending also on the size, some weeks. This one, depending on the years, that some years it stays for 1 to even 2 years, merging with other eddies and traveling here around the Great Island. And also there are some phenomena like eddy splitting, but here, yeah, this one, few months to a year. Well, thank you, everyone.